the process.
Okay, thank you very much. It was very interesting. Oh, I see there is one more question. Gonzalo, yes.
Thanks, Alex. So my question is, so you're considering the case in which you have full thermalization of the system S, if I get it correctly, or it's also like valid for any other?
No, it's not full thermalization. So it lies in this path to thermalization, but it's not full. So in the end, this optimal process will bring this initial state into some thermal state, but this thermal state is not the one in which you prepare your thermal ancilla. So it's the one which has the same non-equilibrium free energy as your initial state. So for example, if you, let's say, if you plot the non-equilibrium free energy as a function of time, for example, you observe a very interesting behavior in which this free energy will decrease and then will increase a little bit, and then to the same initial state that you started with. And then it's a highly non-trivial behavior.
Thank you.
Thank you very much. I think we have to move on to our next speaker. So thank you to be here, Greeshma. Oruganti, so you will be speaking, you are from the University of Maryland and working with Christopher Jarzynski. So we are very happy to have you here, and you're going to speak about the strong coupling of quantum thermodynamics for lattice gauge theory. Thank you very much.
Hi, everyone. Thank you so much for having me here today. It is a pleasure to present the work I did with my collaborators. The title of my talk is Strong Coupling Quantum Thermodynamics for Lattice Gauge Theories, and it's based on a publication in an archive preprint. To put into context thermodynamics and high-energy physics, let's consider heavy ion particle collisions in colliders such as those at LHC and Brookhaven National Labs. The ion packets here smash into each other with extremely high energies and break into very small particles. And right after the collision, these tiny particles enter a phase called pre-thermalization, and then they thermalize locally. These tiny particles start to collide amongst each other to form bigger particles, and eventually these bigger particles will fly away and are detected by particle detectors. We also know that these collision processes generate a ton of heat energy. So the ideas of thermalization, heat exchange, as well as the complex interplay between equilibrium and non-equilibrium phases essentially imply that there are quantum thermodynamic applications in high-energy physics. In a step towards bridging quantum thermodynamics and high-energy physics, we studied the quantum thermodynamics of lattice gauge theories. The best description we have of fundamental particles and their interactions involve quantum chromodynamics, or QCD, and lattice gauge theories are obtained by discretizing space and time, and these offer a way to study QCD non-perturbatively. The Hamiltonian formulations of lattice gauge theories are best suited for quantum simulation experiments, but these formulations are inherently redundant, and to remove these redundancies, one imposes local constraints called Gauss's laws. And these are explicitly implemented in Hamiltonian formulations. From electrodynamics, we know that the electric field flux emanating out of a surface is proportional to the charge enclosed by the surface. Using this, as well as boundary conditions, we fix the gauge in electrodynamics. And similarly, in lattice gauge theories, we use Gauss's laws to fix the gauge. This process can be visualized in terms of the Hilbert space, where essentially the Hilbert space is split into two subspaces, and what we call the physical subspace contains all those states that satisfy the Gauss law constraints. Before we delve into any more details, I want to give you the key takeaways from our work. First, we discovered that lattice gauge theories fall under the paradigm of strong coupling quantum thermodynamics, and I'll make precise what I mean by strong coupling. Second, for a system that's strongly coupled to a reservoir and undergoing sudden quench processes, we define work and heat such that they obey the first two laws of thermodynamics. And lastly, I'll show you an example of this framework applied to a Z2 lattice gauge theory, in which we found that dissipated work signals a phase transition. To give a more concrete intuition for what Gauss's laws are, consider the following toy model, which consists of two spin-half particles. One spin belongs to the system labeled by S, and the other belongs to the reservoir labeled by R. Both of these are governed by the respective Hamiltonians H sub S and H sub R, which are proportional to the Pauli Z operators. These two spins interact via the interaction Hamiltonian, which consists of two terms, which are essentially a product of Pauli operators on either the system and the reservoir. And the combined Hamiltonian of both these spins is the sum of all the terms. The Hilbert space of these two spins is four-dimensional, but in the limit that k, where k is the factor, the prefactor to the first term in the interaction Hamiltonian, in the limit that k goes to infinity, our physical subspace is shrunk down to the two-dimensional basis, space, that's spanned by the up-up, down-down basis. This is exactly how we implement Gauss's laws and lattice gauge theories by penalizing transitions to other states. Although lattice gauge theories contain many more degrees of freedom, the idea of a system that's coupled to a reservoir in gauge theories is embodied by the spin model. A large K also means that the expectation value of this interaction term is at least comparable to the expectation value of the Hamiltonian of the system, which means that the interactions can no longer be ignored while formulating the thermodynamics of the system of interest S. Usually in thermodynamics, we assume weak coupling between S and R and ignore the interactions, but in strong coupling thermodynamics, these interactions play an important role. The simple spin model also illustrates that lattice gauge theories fall under the paradigm of strong coupling quantum thermodynamics. There's recently been a lot of work done on strong coupling quantum thermodynamics, and we draw upon this huge body of literature. Here's the basic setup for strong coupling thermodynamics. We begin with the total Hamiltonian, which is simply the sum of the system, reservoir, as well as interaction Hamiltonians. The general state of the combined system and reservoir is denoted by rho sub S union R, and to obtain the reduced density matrix of the system, rho sub S, we trace out the reservoir degrees of freedom from the general state, rho sub S union R. The equilibrium state of S union R at temperature beta inverse is denoted by pi sub S union R, and it's essentially the Gibbs state under the Hamiltonian H sub S union R. The equilibrium state of the system, pi sub S, is again obtained by tracing out the reservoir degrees of freedom from pi sub S union R. But because we're in the strong coupling regime, it's important to note that pi sub S is no longer the Gibbs state under H sub S. But we can write pi sub S to look like a Gibbs state at temperature beta inverse using this new operator, HS star. HS star is essentially a modified operator, modified Hamiltonian, that acts on the system's degrees of freedom and is defined as -1 over beta times log of the ratio you see on the screen. And this operator, known as the Hamiltonian of mean force, essentially captures the interactions or the effects of the interactions on the equilibrium state of the system. This operator has been used in classical stochastic thermodynamics as well. Because this operator doubles as an effective energy operator on the system's degrees of freedom, it's natural to define the internal energy of the system U sub S as an expectation value of this operator in a state rho sub S. The expectation value here is denoted using trace over the system's degrees of freedom. This definition of internal energy is valid for both equilibrium as well as non-equilibrium states of the system, and is measured entirely on the system's degrees of freedom. Using this operator, the Hamiltonian of mean force, we can also define other thermodynamic quantities such as the free energy, F sub S, which is defined as -1 over beta times log of the partition function Zs star, where Zs star depends on the Hamiltonian of mean force. For equilibrium states of the system, free energy, internal energy, and entropy are related via the standard relation F sub S equals U sub S minus temperature times the entropy S. Upon some algebra, we obtain the entropy of an equilibrium state of the system to be the von Neumann entropy. Now that we have the definitions of internal energy, free energy, and entropy for the system of interest, we can talk about the changes in these quantities for a thermodynamic process. We focus on a class of thermodynamic processes called the sudden quench processes, where the Hamiltonian is changed instantaneously. We begin a process in a global equilibrium state pi sub S union Ri under the initial Hamiltonian H sub S union Ri, and the equilibrium state of the system is pi sub Si. Exactly at t equals 0, we instantaneously change the Hamiltonian from H sub S union Ri to a final Hamiltonian H sub S union Rf. So at times slightly after 0, we have a new Hamiltonian, but the states of the system and the entire S union R are the same due to sudden approximation. From time 0 plus all the way to the final time t sub f, we let the system and reservoir evolve under the final Hamiltonian until they reach their final states. This entire process consists of two stages. The first is around t equals 0, where the Hamiltonian changes, but the state of the system remains the same. And the change in the internal energy of the system due to a change in the Hamiltonian is what we refer to as work. In the second stage, from 0 plus all the way to t sub f, the Hamiltonian remains constant, whereas the state of the system changes, and the change in internal energy due to the change in the state of the system alone is what we refer to as heat. And by construction, the first law of thermodynamics holds. We also analytically proved that W work done on the system is greater than or equal to the change in free energy delta F sub s for this entire process. And if the system were to end up in an equilibrium state, we can recast the second law in terms of heat and entropy as Q is less than or equal to beta inverse times the change in entropy delta S. We now apply this entire framework to a Z2 1+1 dimensional lattice gauge theory that's coupled to spin-half hardcore bosons. We consider a system of 6 sites that's divided into 2 subsystems. The subsystem of interest, on which we intend to define all the thermodynamic quantities, is referred to as a system, and we label it by S, and it contains all the 4 pink sites. The other 2 sites belong to the reservoir or R and are colored in pink. There's spin-half particles that live on all these sites, and these sites are connected via links on which more spin-half particles live. This entire 6 sites and their links are governed by the total Hamiltonian H sub s union R and consists of 4 types of terms. The first set are the matter hopping terms, which essentially tell us that when one spin-half particle hops from one lattice site to another, the spin on the link flips its sign. The next are the gauge field terms, which are proportional to the electric field terms acting on the links. The staggered mass terms are proportional to the number of particles at each lattice site. Due to the sigma plus sigma minus operator at the lattice site, m denotes the mass. And chemical potential terms similarly also are proportional to the number of particles at each lattice site, and mu denotes the strength of the chemical potential term. We now subject this. Oh, I must mention that we have a way of systematically partitioning all these 4 types of terms into a form that's familiar to us, which is H sub s plus H sub r and Vs union R. I'll spare you the details, and I'll jump to the more interesting part of the talk. So we subject our entire system to a quench process that I talked about. The system consists of the same 4 types of terms, and we change the chemical potential term by changing the value of mu from an initial value of 0 to a final value of mu sub f at time equals 0. And for this quench process, we compute different thermodynamic quantities, but I'll focus on dissipated work here, which is work done on the system minus the change in free energy delta F sub s for the entire process. And while carrying out this quench, we keep all other terms of the Hamiltonian constant. We plot dissipated work as a function of the final quench parameter mu sub f, and we see that this black bold curve always stays above 0, essentially verifying our analytical statement of the second law. But something interesting happens with the slope of the dissipated work. Right around a point that I've labeled as mu sub fc, the slope of the curve changes drastically. If we overlay this curve with that of an order parameter, we see some interesting behaviors. The order parameter denoted by sigma is called the chiral condensate, and it has a form that's shown on the screen. We calculate the value of the chiral condensate in the final equilibrium state. And the chiral condensate colored in green is plotted again as a function of the final quench parameter. And we see that this chiral condensate changes its value from a negative value to 0 right around the same time that dissipated work changes its behavior, which indicates that dissipated work qualitatively signals a chiral phase transition in this theory. To summarize the talk, I've motivated that lattice gauge theories, which are integral in high energy physics, can be cast in the language of strong coupling quantum thermodynamics. I define thermodynamic quantities for an open quantum system that's strongly coupled to a reservoir. And for quench processes, I define work and heat such that they satisfy the first 2 laws of thermodynamics. And lastly, I showed you an example of a Z2 lattice gauge theory in which dissipated work signaled the phase transition. I'd like to thank all my wonderful collaborators. It has been a pleasure to work with Zora Dawoodi, my advisor Chris Jarzinski, Nicholas Mueller, Connor Powers and Nicole Younger-Halpern. Connor was the primary force behind all the numerical Z2 lattice gauge theory calculations. I'd like to acknowledge my funding sources. And thank you all so much for your attention. I'm happy to take any questions you have.